Hello everyone, I am Bitan Chakraborty from EC department from Veltech University, final year student. I did my final year project in France, Paris at IACP under Professor Shun Zhang. My project was to implement second order blind identification in FPGA to perform real-time blind source separation. What my project was, basically it was to analyze the EEG signals, or in the sense, or in the other hand, brain signals, what the signals which we get from the brain. And the algorithm which I used for analyzing the EEG signals is second order blind identification, or SOBI algorithm. It depends on how for an example, if we go to a cocktail party and we don't know someone and we try to find someone and we don't know his or her name or anything else, but still we try to find him or her by only knowing the physical feature of that person. What we do when we go to a cocktail party in those kind of situation is that we try and we have a reference in our mind, we keep that constant and we try to compare that constant with all the other people. And so that is the main theory which we have taken and made use of it in SOBI algorithm. Now I'll try and show you three presentations which will tell you almost what I did in my project, and I hope you'll understand. So let's enjoy. So as you can see in the first slide, I'm showing you introduction about EEG. So what is EEG? EEG is the full form of EEG is electroencephalography. It measures the activity, cortical activity. It also used to monitor the electrical activity within the human brain, spatial distribution of the changing voltage fields over time. One of the most widespread brain mapping technique. Its applications are to research and clinical. In the next slide, I'm going to show you the recording setup. This was one student in ESPCE, which is another university which had its collaboration with IESEP, and she was a student, medical student, biomedical engineering student from Manchester University, and she helped me with my project. As you can see, we have placed on her head electrode which has the resistance less than 5 kilo ohm. These are the recording signals, and this is an amplifier which is used to amplify the EEG signals, because the signals what we are getting is very faint and it is easily engulfed by noise. So we have to use an amplifier to amplify the signal. Now these are the signals what on the screen, on the computer screen which you are seeing are the recording EEG signals. Now in the next slide, I'm going to show you what are the issues. These EEG signals are mainly affected by artifacts due to muscle activity, eye blinks, electrode movement and electrical interference. By this point, what I meant is these EEG signals what we are getting from our brain are so faint that they get easily affected by artifacts like any kind of RF signals, whatever there are in the surroundings, or noise signals, and many other things, like we are moving our muscle, we are moving our hand, and by doing that we are moving our muscle, so it gets affected by that. If we are blinking our eyes like this, then we get a different signal. Electrode movement, because the electrodes are not placed statically, it has to be perfectly ideal for getting a perfect EEG signal. Then the next issue is that EEG amplitude. Here you can see we are getting the signals in microvolts, hence it is easily masked by artifacts. Recorded EEG, linear mixture of the original source signals, artifacts and noise. Actually by this point what I meant is that the signal which we actually get after recording is mixed with lots of different other RF signals, noise and many more artifacts. So our basic aim for this project is to try and minimize those artifacts and remove those artifacts as much as we can. So this is the actual recorded signal with blink artifacts. Means these are the type of signals which we will get in actuality if we blink our eyes. Now, artifact detection and removal. This is a very important issue in EEG signal processing. Lot of ongoing research is going on. Conventional method, averaged or processed so that artifacted portions are rejected or cancelled out. Which means, by this point, it means that we cannot remove the artifacts totally or make it zero, but we can average it out and try and make it nullify so that we get a better signal. Now, however, this is not possible for real-time applications like brain-computer interface or clinical neuro monitoring. For all these days, what we were trying to do is, first we used to record the EEG signals, then we would analyze it later on, but that would be very much time consuming and it's not practically useful. Like, if we want to get a perfect signal at the time of recording, then it would be very difficult. So for that, ongoing researches are going on, and I'm just trying. It's not, I was not sure at the beginning of the project whether I will get a perfectly clear signal or not. So I was just trying. Future of EEG, online EEG, which means that, in the last point, this means that online EEG means that at the time of recording the EEG signal, you will get a perfect signal without noise and everything else. Now, in this slide, based on the algorithm, I have designed one block diagram which states that what are the types of works which needs to be done so that we get a clean EEG. So basically, we have the recorded, or you can say the specimen or the recorder or the recording area from where we are getting the recorded signal. Then it goes via an amplifier. Then we have this BSS block, which is the blind source separation. Then class in ER for detection, artifact detection. Then we have BSS, and then we have the clean EEG. In this slide, I am showing you how to implement it on FPGA, field programmable gate array. So you can take the signals which are coming out from this block, as you can see. From this block we will get the clean EEG signal and we can implement it on FPGA. And this part we'll see it in the later portion of our slide of my presentation. Now, why FPGA? Why did we choose FPGA? Because it provides optimal parallelism environment, faster and real-time solution. Now, the hypothesis behind implementing FPGA is that implementation in FPGA hardware could improve the performance of the system in terms of speed, because as we all know that FPGA provides a lot of speed. Now, the objective of how to implement it and the objective behind why are we implementing it on FPGA. Implement blind source separation algorithm in FPGA to verify if there is a performance improvement in terms of speed. This point you will understand and later when I present you the later portion of my presentation, because there is a comparison between BSS algorithm and ICA, which is independent component algorithm, and then you will understand that why I am using BSS blind source separation algorithm, not ICA, because and it is just to prove that BSS algorithm is better than blind source algorithm. Now the conclusion, if the chosen algorithm is a good choice for FPGA implementation, real-time application and EEG source separation. These are the three conclusions which I will try to come at the end of my presentation. Now, what is blind source separation? Now, recovering the source signal from a linear mixture of signals. It reduces mixtures to components that are in some way independent of each other. Similar to the cocktail party problem which I mentioned in my previous at the beginning of the video. Now it works on a simple equation: x is equal to a cross s. Now what is x? X is the measured EEG signals which is mixed with noise and all the other artifacts. S is the original EEG signal matrix, like what we have as reference or the constant. Now A is a mixing matrix. Is the mixing matrix which we are introducing it forcefully. Now blind, since both A and S are unknown, we don't know. That's why it's called blind source separation. Since A and S, we don't know anything like what we have in A and what we have in S. See, but even though we know something what we are supposed to get in S, but even though we don't know anything, that's why it's called blind. Now BSS algorithm, no general consensus about any BSS algorithm being the best. I'm not saying that it is the best algorithm, but to me, I thought it was the best. Independent component analysis, ICA algorithms, widely used. That's why I tried to venture out in a new variety of algorithms. Let's see what we can do in BSS algorithm, because nobody has worked on this algorithm so far. Now, based on theoretical analysis and literature surveys, the choices were narrowed down to FastICA, Infomax, and SOBI. Now, under BSS, we have these three algorithms, which are FastICA, Infomax, and SOBI. And among these three algorithms, I preferred SOBI, which is a second order blind identification. Now, I'll show you in this slide comparison of algorithms based on experiments. Concept of